So let's look at an example. And the example that Wessel gives is example 1-10. And here we're given information that the strength of olivine, measured as Young's modulus, this is this is a measure of the elastic stiffness of olivine. And we're told that a variety of studies have shown that the mean value of Young's modulus, and Young's modulus is denoted as capital E, so the mean value is 1.010 times 10 to the 11th pascals. And of course, the olivine Young's modulus varies, and the variation is characterized by the standard deviation of 1.0 times 10 to the 10th pascals. So that's about a tenth of the mean. So the question is, what is the probability, big P, of E falling between 9.8 times 10 to the 10th and E, so E being greater than 9.8 times 10 to the 10th, and E being less than 1.1 times 10 to the 11th. Okay, so the first thing we got to do is convert E to normalized values. And so our normalized value is Z again, and that's E, the difference of E from the mean divided by the standard deviation. And we get a range. The range in question is minus 0.2 to 1.0, right? So this is equal to the mean, so that's 1, and this is less than the mean, so we get a negative number. It's 2/10 of a standard deviation. And so the second part of the problem for solving the problem is just to evaluate the probability of Z being greater than 0.2 and less than or equal to 1, and that's equal to 1/2 times ERTH1 over the square root of 2 minus ERTH, the error function of minus 0.2 divided by the square root of 2, and the answer is 0.4206. So that's 42.06%. We have a 42% chance of finding an olivine within this range, with an olivine with a Young's modulus within this range. Another example that Wessel describes, is the fact that the normal distribution approximates the binomial distribution for large N. Or really when NP is large, and large being defined by greater than 5. or 1 minus NP times, oh, I'm sorry, it's 1 minus P times N greater than 5. And you can go through and, okay, well, let me go ahead and write that out. So the way we approximate the binomial distribution with the normal distribution is we would set mu is equal to NP, and sigma, well, I should write about equal to NP because it's approximate. It's a good approximation for some cases, but it's still approximate. And this defines sigma in terms of the quantities of the binomial distribution. And so again, the binomial distribution of x is equal to, in parentheses, n over x times 1 minus little p, for the probability of one success, or actually 1 minus p is the probability of one failure raised to the n minus x power, and little p raised to the x power. And that's about equal to, again, 1 over sigma times the square root of 2 pi times the exponent of minus x minus mu over sigma squared, they're both squared, all over 2. Again, with mu and sigma defined as above. And let's look at this here. We'll draw up our show our MATLAB example. So here I'm going to make for a binomial probability distribution, let's make n equal to something big. So we'll make it equal to 50. And we'll run our script. Okay, so we get this binomial distribution. We looked at that originally. And I just happen to have this set up so we can make a visual comparison between the two distributions. So you can see visually that the Gaussian distribution looks very similar to the binomial distribution. So the Gaussian distribution, which is continuous, is a reasonable approximation to this binomial discrete distribution for this special case. Another example that Paul gives is the Poisson distribution, which is another continuous distribution, but it's a good approximation to the binomial distribution when little p is very small and n is very large. So the probability distribution for x is well approximated by the Poisson's distribution, and that's lambda raised to the x power e to the minus lambda. This is a x all over x, and x is equal to 1, 0, 1, 2, all the way up to n, where lambda is equal to n times p. And for example, large earthquakes volcanic eruptions, large floods, but probably not power outages. These three items are at least have been shown to follow a Poisson's distribution. So I encourage you to continue reading through Wessel's chapter to look at some other continuous probability distributions. But I'm going to conclude here, and this will conclude our video series on Introduction to Statistics.